Are there any other questions about groups, which is the topic of great interest? So we've only been looking so far at abelian groups. The next lecture will be on examples of non-abelian groups, but abelian groups themselves are very nice. In general, this just to remind you or mention a few things. If G is a group, doesn't matter whether the group is additive or multiplicative, doesn't matter whether the group is abelian or not abelian. Just note this. So the number of elements in the group in G is called the order of G and denoted by G with absolute value signs around it. So for example, if you take the set of integers as an additive abelian group, of course that's infinite. There are infinitely many integers. If you take the congruence class is mod 2, that has order 2, has 2 elements. If you take the multiplicative group of congruence class is mod 8, that has 4 elements in it, and so on. So that's the order of a group. Now, in group theory, the word order is used in 2 different ways. So this is the first definition. It's the order of a group. But an element in a group also has an order. So let X be an element of G. So you can look at the sequence of powers of X. X squared, X cubed, X to the 4th, and so forth. And we say that the element X has order n if X to the n is the identity in the group and n is the smallest positive integer with this property. So for example, if G is the group of congruence classes mod 5 that are relatively prime to 5, so this is 1 plus 5z, 2 plus 5z, 3 plus 5z, and 4 plus 5z. Every element in this finite group has an order. So let me write it on another page so I have a little bit more room. So 1 plus 5z to the first power is 1 plus 5z. So 1 plus 5z has order 1. In fact, the only element that has order 1 is the identity element in a group. What about 2 plus 5z? Well, 2 plus 5z squared is 4 plus 5z. 2 plus 5z cubed is 8 plus 5z, which is 3 plus 5z. 2 plus 5z to the 4th is 16 plus 5z, which is 1 plus 5z. So finally, we get 1 plus 5z. So 2 plus 5z has order 4 in this group. What about 3 plus 5z? Well, if you take the powers, 3, 9, 27, 81, the first time you get to something which is 1 mod 5 is the fourth power. This is 81 plus 5z, which is 1 plus 5z. So 3 plus 5z also has order 4. And 4 plus 5z, if you square it, that's 16 plus 5z, which is 1 plus 5z. So 4 plus 5z has order 2. So in the group of congruence classes mod 5 that are relatively prime to 5 in that multiplicative group, there's one element of order 1, two elements of order 4, and one element of order 2. That's the order of an element. Now, in an additive group, G, if you take element X and G, you do addition. X plus X, you have 2X. You have X, 2X, 3X, and so forth. And the order of X is the smallest positive integer n such that n times X is equal to the identity. Now, I have to emphasize the fact not every element in a group has a finite order. I'll give an example of that in a minute. But this is the definition of the order of an element in an additive group. And let me look at an example. Suppose we let G be the integers mod 5. That's a nice example. As an additive group, that has 5 elements, not 4. 5z, 1 plus 5z, 2 plus 5z, 3 plus 5z, 4 plus 5z. So what are the orders of each of those elements? Well, 1 times 5z is 5z. That's the identity. So 5z has order 1. What about 1 plus 5z? Well, you add it to itself. You don't get 0 until you add it to itself 5 times. So 1 plus 5z has order 5. What about 2 plus 5z? You start adding it, when do you get 0? You had 2, 4, 6, 8, 10, 5. 3 plus 5z. You also don't get 0 when you add it to itself until you've done it 5 times. And the same with 4 plus 5z. So each of these elements has order 5.
Professor, can you explain the difference between this and cardinality? And if
Cardinality is the number of elements in a set. It has
okay.
nothing to do with, cardinality has nothing to do with the group. Cardinality, any set, the number of elements in the set is the cardinality. Now for a group, the cardinality of the group, the number of elements in it is the order of the group. So for a group, cardinality and order mean exactly the same thing. But now I'm talking about the order of an element. So this is not, so this has nothing to do with cardinality.
Thank you.
Let's look at another example, an additive example. Suppose we take the integers mod 6. So we have 6 congruence classes, 6z, 1 plus 6z, 2 plus 6z, 3 plus 6z, 4 plus 6z, and 5 plus 6z. And we have to add them up and add them to themselves until we get 0, which is 6 plus 0, 6z. So 1 times 6z is 6z. So 6z has order 1. 1 plus 6z, when you add it to itself, you don't get 0 until you've added it 6 times. So 1 plus 6z has order 6. What about 2 plus 6z? Well, you get 2, 4, 6. When you add it to itself 3 times, you get 6 plus 6z, which is 0 plus 6z or 6z. So 2 plus 6z has order 3. 3 plus 6z, well, you add it to itself twice. You get 6 plus 6z, which is 6z. So 3 plus 6z, this has order 2. 4 plus 6z, when you add it to itself, you go 4, 8, 12. Aha, 4, 8, 12, 3 times. 3 times 4 plus 6z is 6z. So 4 plus 6z has order 3. 5 plus 6z, how often do you have, how many times do you add it to itself to get 0? 5, 10, 15, 20, 25, 30. You have to add it 6 times. So 5 plus 6z has order 6. So in the additive group of integers modulo 6, you have one element of order 1, one element of order 2, 2 elements of order 3, and 2 elements of order 6. That's kind of interesting. Suppose we take G to be the integers, the additive group of integers, and let X be 1, just the number 1 in Z. So when you add 1 to itself, you get 1, 2, 3, 4, 5. When do you get 0? Well, you never get 0. So 1 has no finite order. We say 1 has infinite order in the group. And in a multiplicative group, let's take, for example, in the multiplicative group of the non-zero rational numbers, let X equal 2. So when you start to take the powers of 2, when do you get 1? Never. No power of 2 is equal to 1. So 2 has infinite order in the rationals. Suppose you take X equal minus 1, and you start taking the powers. Minus 1 squared is 1. So minus 1 has order 2 in the multiplicative group of rational numbers. Okay? Suppose we let G be the non-zero complex numbers. Suppose we let X equal I. What are the powers of I? You have I, the first power is I squared is minus 1. I cubed is minus I to the 4th is 1. So I has order 4. Suppose we let X equal, I don't know, minus a half plus the square root of 3 over 2 times I. What is the order of X? So you have to know how to multiply complex numbers, but by the time you take math classes at this level, you know the complex numbers. That's what X is. What is X squared? Well, if you multiply it by itself, you get minus a half minus root 3 over 2I. If you cube it, you get 1. So X has order 3 in the multiplicative group of complex numbers. So these are simple examples of orders of elements in abelian groups.
I'm sorry, Professor, can you please go over the exact definition of a ring again? I'm having a little problem
Okay, well,
organizing that.
I
Thank
can,
you.
but right now, and for the next quite a long time, we're just going to be talking about groups. A ring,
Oh, okay, no problem.
no, but a ring is just, there's nothing to even think about. It's just a definition. In a ring, you can add and you can multiply. And under addition, you have an additive abelian group. It has the properties of being a group. Multiplication is not a group, that's usually, but never in fact. But multiplication is associative, and there's an identity, and you have a distributive law. But for the rest of this week, I think we're just going to be talking about groups.
Okay.
I have another question about isomorphism.
Yep.
If I know that if something is isomorphic, then if a function is isomorphic.
Well, no, okay. If a function is an isomorphism, yes.
Yes. All right. Yes. Thank you. Oh, actually, I'm sorry. Never mind. I'm sorry.
So the groups we've talked about today, the examples, they've all been abelian, but there are also nice examples of groups that are not abelian. So you should know about matrices, A, B, 2 by 2 matrices. If you have two 2 by 2 matrices, you can multiply them. Right? That's the formula for matrix multiplication. It's row into column. And the determinant of a matrix that's say A equal to A, B, C, D is, you write determinant of A, it's AD minus BC. And you can prove that if you take the product of two matrices, A times B, the determinant of the product is the product of the determinants. So if the determinant of A and the determinant of B are both equal to 1, then the determinant of AB is determinant A, determinant B. It's 1 times 1, or 1. So if we there's a classical notation, SL2 of Z. So it's not so important what this means. It means something, but this is all the matrices A, B, C, D, where you only have to look at integers for the coordinates. And the determinant is always equal to 1. So for example, that's a nice example. This is a matrix in SL2Z, because what's the determinant? The determinant is 7 times 8 minus 5 times 11, 56 minus 55, that's 1. So this is an example of a matrix in this set. And this product rule for the determinant says that SL2Z is closed under matrix multiplication. Because if you take two matrices of the determinant of 1, the product has determinant of 1. So this set is closed under matrix multiplication. And you can check, or I know linear algebra is supposed to be a prerequisite for this course, but matrix multiplication is always associative, no matter what the sizes of the matrices. And there's an identity. The identity in SL2Z is the matrix I equal to 1, 0, 0, 1. This matrix has determinant 1, and you multiply this by anything, and that you get back that anything. And what about the inverse? So if A is equal to A, B, C, D, then let's see, so this means that A, B, C, and D are integers, and the determinant is 1. Suppose I define B to be, I don't know, D minus B minus C, A. So this is the determinant of A. What's the determinant of B? Well, it's also AD minus BC. It's AD minus B times minus C, that's BC. This is also 1. So if you take this matrix is also in the group. Let's compute AB. So A, B, C, D, D minus B minus CA. When you do the calculation, you get the matrix AD minus BC minus AB plus AB, CD minus CD minus BC plus AD. That's exactly 1, 0, 0, 1, which is the identity. So given this matrix A, this matrix B is the inverse. Actually, I have to check that BA is also the identity, but it's the same calculation. So that's kind of nice. So this is a group.
Professor, that's a group, but it's not a commutative group because multiplication is not commutative, correct?
Exactly. So so let me just take two sort of randomly simple matrices. Suppose I take, I don't know, 2, 1, 5, 3, call that A, and that has determinant 1. And B is maybe minus 2, yeah, let's make it more interesting maybe, I don't know. 1, 4, maybe 3, 5, 7, 2. So these both have determinant 1. This here, the determinant of A is 6 minus 5, or 1. The determinant of B is 15 minus 14, which is 1. So if I compute AB, I get 6 plus 2, 14 and 5, 15 and 6, 35 and 15. And again, you can check this matrix has determinant 1. What's the determinant of AB? It's 8 times 50 minus 21 times 19. This is 400. This is 399. It's 1. What about BA? 3725, 2153. So this is 6 plus 35, 41. 3 plus 21 is 24. 4 and 25 is 29. And 2 and 15 is 17. Well, they're different. So SL2Z is a non-commutative, non-abelian group.
Is SL2A an abelian group for addition?
It's no. You can, if you add two matrices of determinant 1, you do not get a matrix of determinant 1. So this is not closed under addition. You can add matrices, but SL2Z, if you take the sum of two matrices in SL2Z, you do not get another matrix in SL2Z.
Thank you.
So that's a nice group. Let's see. Here's a very simple element. Suppose I take A to be the matrix 0, minus 1, 1, 0. So that's an SL2Z because it has determinant 1. 0 minus minus 1. What's A squared? I get minus 1, 0, 0 minus 1. What's A cubed? So A cubed is A times A squared. So that's 0 minus 1, 1, 0, minus 1, 0, 0, minus 1. When I multiply them together, I get 0, 1, minus 1, 0. What is A to the 4th? So that's A times A cubed. So that's 0 minus 1, 1, 0 times 0, 1 minus 1, 0. I get 1, 0, sorry, I get, oops, something's wrong. Let me just double check. So A squared is this. A cubed is A times A squared. 0 minus 1, 1, 0. And that times A squared. So that's 0, 1 minus 1, 0. A to the 4th is A times A cubed. So A is 0 minus 1, 1, 0. A cubed is 0, 1 minus 1, 0. When I multiply them, I get 1, 0, 0, 1. I get the identity. So for this matrix, A to the 4th is the identity. So A, this particular matrix A, has order 4 in the group SL2Z. SL2Z itself is an infinite group, so it does not have finite order. But in any case, the notion of the order of an element and the order of a group, these are very important in group theory.
Professor, on this topic of matrices, I actually had some questions with today's homework.
Okay.
Should I read it out, or do you have it in front of you?
Yep.
Okay, it's question number 3, parts A and B. Part 3A gives you a matrix. It defines a 2 by 2 matrix. Matrix A equals 1A, 0, 1.
Mm-hmm.
And it says to prove that matrix A times matrix B equals matrix A plus B. And I actually wrote out the proof for the left and the right-hand sides, but I'm just trying to figure out why it's not looking the way it should.
Well, let's see. So I define the matrix M sub A to be 1A, 0, 1. By the way, you just notice that this matrix does have determinant 1, so this is in SL2Z. We don't need that, but that's just an observation. So if you multiply MA times MB, that's 1A, 0, 1 times 1B, 0, 1. So when I multiply, I get 1 B plus A, which is A plus B, 0, 1, which is M sub A plus B. So I think that's the calculation you were asking about.
Because then I took the right-hand side of the equation and I just added A and B together.
I'm not sure what you mean.
So I
The
would
right-hand
write
side
of the proof. So the left hand would be matrix A times matrix B on the left-hand side equals matrix A plus B.
right,
So
that's what you're supposed to prove.
Okay, I was under the impression that I had to add A plus B on the right-hand side, where you just put on the right-hand side of the equal sign.
I'm not quite sure. So MA is a matrix, MB is a matrix, and I need to
Right.
multiply the two matrices. So when you
Right.
multiply a 2 by 2 matrix times a 2 by 2 matrix, you get another 2 by 2 matrix. You don't get a number. And then you observe that this 2 by 2 matrix is exactly this guy. And that's what we wanted to prove, that MA times MB is M, A plus B.
Okay, maybe I was just going off on a tangent somewhere.
Right. I mean, so it's supposed to be very simple.
Right, I probably made it more complicated than it was.
Well, yeah, people do that.
Also with part B, I needed some help.
Oh, okay. So what I'm saying is let H be the set of all matrices of the form M sub A for every integer A. So this identity proves that, so this identity star, this equation, proves that H is closed under multiplication. What about associativity? If you take two matrices and multiply them together, and then multiply by a third matrix, this matrix is MA plus B times MC. So that's M of A plus B plus C. But A plus B, A, B, and C are integers. So A plus B plus C is the same as A plus B plus C. So this is MA times MB plus C, which is MA times MB MC. So this is the associative law. So the multiplication satisfies associativity. The identity matrix 1, 0, 0, 1, that's just the matrix M0, where you have a 0 in the upper right-hand corner. So that's in H. And if I take a matrix A and I multiply it by A, M sub, if I take the matrix MA and I multiply it on the right by M minus A, that's MA minus A, which is M0, which is the identity. And similarly, M minus A times MA is M0, which is the identity. So the inverse of the matrix MA is another matrix M minus A, which is an H. So this set of matrices is closed under multiplication. The associative law is satisfied. There's an identity, and every element has a multiplicative inverse. So it's a group. And MAMB is MA plus B, but A plus B for integers, A plus B is B plus A. So this is MB times MA. So this little calculation just checks that this is in fact an abelian group. Does that make sense?
Yes, thank you very much.
Okay. Anything else I can help you with this afternoon? Well, okay. If not, then I guess we can quit for the day. We'll be here tomorrow morning at 11 o'clock. Hopefully in a finite time, I will finish grading the homeworks, sorry, grading the exams. And as soon as I do, I will go over the exams in one of these problem sessions. Okay. That's it then.
Thank you.
Bye. Bye, everybody.